Hi there, folks. Today we're looking at areas of regular polygons, all right? And a regular polygon, remember, is a polygon where all the sides are congruent and all the angles are congruent as well. So one of the regular polygons we've looked at extensively would be something like an equilateral triangle. All the sides are congruent, all the angles are 60 degrees, all right? Or a square would also be a regular polygon because all the sides are congruent and all the angles are the same. They're all 90 degrees. All right, and so as we kind of expand out, we already know how to find the area of a triangle and a square, but now as we kind of expand out to things like pentagons, all right, and hexagons and heptagons, all right, we need something else. And rather than have a formula that we measure for each of those individually, we have one formula that covers all of them. All right, and it requires two things. So there's two things we need to talk about here. One is the radius of a regular polygon. And the radius is the distance from the center to one of the corners, to the vertex on this polygon. And really, when you think about it, like the radius of a circle goes from the center to the outermost edge of the circle, to the circle itself. And so the same thing's happening here. We're going to the outermost edge, but the outermost edge is a point, all right? It's a vertex on this thing. And then we also have the apothem, which is the a perpendicular measurement of the distance from the center to one of the sides. So again, the radius is measuring from one point to another point, all right, from the point in the center to the point of one of the vertices, all right? But the apothem is measuring literally the distance from the center to one of the sides. And when we measure the distance between two things, we always measure at a right angle, all right? And so the apothem is the perpendicular distance from the center to the side. So here's what they look like kind of in the context of this one is a hexagon. And so we can see the radius is a little bit longer in terms of this thing, and that's typically how it's going to go because, of course, that radius, the vertex, is always going to be further from the center than the actual side is going to be, all right? When we measure the distance to the side, we measure perpendicularly, all right? So the radius goes from the center to the vertex, and the apothem goes from the center directly to one of those sides, all right? And when you think about the radius, you know, that should be easy to remember if you were to kind of put a circle around this thing. That was terrible. That was terribly done. But the radius of the circle that kind of goes around this shape is the same as the radius of the polygon itself. All right. So the radius is to the point. The apothem measures to the side, to the segment. Okay. And so it says, find the measure of each angle. And so this becomes important. What we're going to do is we're going to use angles and segments and eventually trig to find the different pieces of this thing that we need, to find things like the radius and the apothem in order to find the area of this. So let's practice finding some of the angles first. And some of these things, again, they're broken into triangles. And so once we break it down into triangles, we can find each of those triangles and find all the measurements that we're missing here. All right. And so the first thing we have to start with is the fact that this thing is a pentagon. All right. And so because this thing is a pentagon, we're going to use our formula here. Remember the 180 times n, which is 5 minus 2. And so the total of the angles inside the pentagon are going to be the 180 times the 3 here, which is 540. So that's the measurement of all of these angles added together, which means that because this is a regular pentagon, I just have to divide that by 5, and it gives me the measure of each of these entire angles. So if I divide by that by 5, that gives me 108 degrees. And again, that's for this whole thing. But because this is a regular polygon, once again, I know that what's going to happen here is each of the radii are going to be the same. So each of so this radius will be the same as this radius, same as this one, same as this one, same as this one. So really, this is a bunch of isosceles triangles, which means that these angles are being bisected. This one here, angle 3, has to be the same as this one here. And so if the whole thing is 108, each of those pieces is going to be a 54. Okay, and so I kind of started on the outside here. I started with angle 3, but this is 54 degrees. And really, every single one of these little angles is 54 degrees. And so I can kind of fill this in the whole way around. I'm going to go ahead and stop there. But if I kind of fill that in the whole way around, those are all 54 degrees. Well, that allows me to find the angle towards the center as well. So now I can find angle 2. Because remember, the angles inside of a triangle add up to 180 degrees. So when you kind of look at that guy, because I have the 54 and the 54, which again was the 108, I can kind of just do a little subtraction there, and ends up being a 72-degree angle in that center. Okay? So this one is 72 degrees. And really that means that all of those center angles are 72 degrees. Okay? So this one's 72 degrees as well, and this one's 72 degrees. And even this whole angle right here is 72 degrees. However, I've dropped a perpendicular line through that triangle. And remember, when I do that with an isosceles triangle, which is what each of these is going to be, it bisects that angle. So that means that if I want that whole thing to be 72 degrees, that this little piece is 36 degrees. Okay? And so kind of expanding back out here, the measure of angle 1, well, that was 36 degrees. The measure of angle 2 was 72 degrees. And the measure of angle 3 was 54 degrees. Okay? And angle 1, I could have actually filled in the 54 degrees here as well, and then said, hey, the 3 inside there add up to 180 degrees. Okay? But finding those angles is going to be really important, because then we'll use those angles and the triangles that we've kind of just talked about here to find those missing pieces, to find the missing sides of this thing. Again, using things like the Pythagorean theorem or using our trig functions eventually. Okay? If we look at this one, again, I want to find all of these. So once again, this one is an octagon this time. So because it's an octagon, again, I do the 180 times n minus 2 to find the measurement of all of those angles together. So all the interior angles, so 180 times the 6. And that gives me 1,080. Again, that's all of the angles added together. If I want each angle, I have to divide that by 8. And so that gives me 135 degrees for each of those individual angles. So like this whole angle is 135 degrees. This whole angle is 135. This one, 135. Okay, each of those is 135, which now allows me to find angle 3. Well, angle 3 is just going to be half of that. Okay, because these two angles are being bisected. This angle is being bisected because of the fact that these have to be isosceles triangles. All right, I just have to divide by 2. So if the whole thing is, if one of these whole angles is 135, it means that angle 3 has to be a 67.5. Okay, it has to be half of that guy. All right. And then using that same knowledge here, if each of these is 67.5, well, now I can find angle 2 as well, because once again, I'm inside a triangle here, and the value, the angles inside a triangle add to 180. So that means that angle 2 has to be a 45-degree angle, which is then true for all of these angles that are in here, 45 degrees, and even true for this entire angle, which 1 is part of that entire angle. And once again, because of the perpendicular line that's being dropped here, it means that angle is being bisected. So angle 1 is just half of that, half of angle 2, half of that 45-degree angle. Okay, and so that's going to be the 22.5. So let's write all these down. Let's see. The measure of angle 1, 22.5 degrees. The measure of angle 2 is 45 degrees. And the measure of angle 3 is 67.5 degrees. Okay? And again, you're looking at that thinking, well, how does that help us? Eventually, that's going to allow us to find those missing pieces, to find the radius of the polygon, and to find the apothem. Okay? And so here's our actual area formula for a regular polygon. And this will work for things like a square, okay? A square is a regular polygon. It'll work for things like an equilateral triangle. However, we don't typically use those because we have an easier method for squares and equilateral triangles. Squares just base times height. triangles are 1/2 the base times the height, okay? But this will work for any regular polygon. It's the area equals 1/2 the apothem times the perimeter, okay? And that's what that P stands for, all right? And so there's a lot of different pieces going on here. And you may be wondering, well, why did we even discuss the radius? Well, the radius will come into play because it'll allow us to find some of these pieces. The radius will help us find the apothem. The radius will help us find the side measurement of the shape sometimes, and that'll lead us to the perimeter, okay? So the radius becomes kind of a stepping stone within here to help us find those missing pieces, all right? So again, 1/2 the apothem times the perimeter, all right? And that's the piece that students usually forget. They forget to do the perimeter for that piece. Instead, they end up using just one of the sides or something like that. But again, because it's a regular polygon, once you have one side of the polygon, you have all the sides, okay? And you can find the perimeter pretty easily by doing some multiplication, all right? So 1/2 the apothem times the perimeter. For example, if I look at this guy, it says find the area of each of these. So I'm going to find the area of this guy. And so again, we have to start with, all right, well, how do I find these different pieces? I have the apothem, and I have the one of the side lengths. And the thing is, we kind of have to assume here, I didn't say it in the directions, but let's assume that this is a regular polygon, all right? And so because this is a regular polygon, if I have one side, I automatically have all the other sides, okay? And so, again, I have the apothem this time is the 12.3. The only thing that I'm missing is the perimeter, okay? And so, really, if you just count up the number of sides, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So because there's 10 sides, each side is 8 inches, well, you can easily find the perimeter and say, hey, the perimeter is 80 inches. Okay, now I have all the pieces that I need to find the area. The area is 1/2 the apothem, which is the 12.3, times the perimeter, which is the 80 inches. Okay, and then what happens here is really this just becomes a job for my calculator. All right, let's just plug it in. So the 1/2 times the 12.5 times the 80, and that gives me, sorry, I hit the buttons wrong. Let me try again. I hit 12.5 instead of 12.3. I think I might have even said 12.5. Shame on you, Mr. Jansen. Okay, so I get 492. And again, that's square inches. Okay, and so again, we just need the apothem and the perimeter. Eventually, we'll get to some more difficult ones where we're not just missing like the perimeter. We might have to find some of these angles to help us find some of the measurements, all right? If I look at this one, once again, I'm given the apothem. I can see that the apothem is 8 centimeters. The only thing that I'm missing is the perimeter. So I have to find the piece of this thing that I'm missing. And really, since I know that this is 11.6, if this is a regular polygon, well, it means all the sides are 11.6. Okay? So once again, if I want to find the perimeter this time, well, it's just 5 times 11.6. You don't have to do 11.6 plus 11.6 and do that 5 times. Just use a little bit of a shortcut. Use a little bit of multiplication here. Okay, so I get 58. That's the perimeter. And so now the area, once again, is 1/2 the apothem times the perimeter. And again, I can do this on my calculator. Okay, so that gives me an area of 232, and again, that's centimeters this time squared, so square centimeters. Okay, so again, 1/2 the apothem times the perimeter. If I look at this guy, we're not quite ready to use trig yet, but this one we can still find the apothem, which is kind of one of the things we're missing here, without using trig. But we're just going to kind of look at the angles and kind of figure this out in terms of little triangles, okay? Just like we did in some of those previous examples. And so for this one, once again, if it's a regular polygon, I know that all the sides are 3, all right? And it's a hexagon this time, so there's 6 sides. So I can easily find the perimeter. That's an easy thing that I can find. It's just 3 times 6. And so the perimeter on this one is 18 millimeters. Okay, so I have the perimeter. That's one of the things I was missing. But now I need the apothem. And that's a little bit more difficult. And so let's draw the apothem first. So let me draw that guy. So here it is. That's what I'm looking for. I'm going to call it A. And so what I'm going to do here is I'm just going to actually draw all the radii for this one. And if you do that, what it does is it gives us a bunch of triangles. And now I can use the fact that, hey, I know what the angle measurements are for this thing. If I do the 180 times n minus 2, it tells me that all the angles inside here add to 720 degrees. But because this is a regular polygon, all of them are going to be equal. So each of these, like this whole angle right here, is 120 degrees, which means each of these little angles must be 60 degrees. And so as I kind of work my way around this triangle, if this is 60 degrees, well, that means this one's also 60 degrees. So this is a bunch of equilateral triangles. Well, now come down here to where I've drawn the apothem. That's a 90-degree angle. And we know that this guy is a 60-degree angle. And then we know that this guy is a 30-degree angle. So once again, what I have is a 30, 60, 90 triangle. And, there's a couple ways you can think about this. You can think about this as like, if this whole side right here is 3, well, then this side right here is also 3 because of the equilateral triangle, which means that this missing piece right here is 1.5. You could also just look at it and say, hey, if I look at that original equilateral triangle, once I drop that perpendicular, it bisects that base segment. So the 3 gets bisected into the 1.5 and the 1.5. And so I have the radius here. I have that the shorter side of the 30, 60, 90. But what I need is the apothem. Well, that's the longer side of that 30, 60, 90 triangle. Remember, I take the shorter side times root 3 this time. Okay? And so now I have the length of the apothem. I have the perimeter off to the side. I did that a while ago. So area equals 1/2 the apothem times the perimeter, which is 18. Okay? And so if I asked for this in kind of exact terms here, it would be 1/2 times the 18 times the 1.5. So just multiply the stuff on the outside. So 13.5 and then a root 3. And so in terms of exact terms, we don't typically write a decimal with a radical. We would typically write it kind of like this. We'd probably change this to an improper fraction. So 13.5 is really 27 over, 27 over 2. So I could write it as 27 root 3 over 2. And essentially that's the same thing. Okay, and so here's the exact version of this thing. Why would we want the exact version? That's an excellent question. We probably won't. So the rounded off version this time, let me plug that into the calculator, gives me about a 23.38. And again, it's square millimeters. Okay, so again, really, finding the area itself is not difficult for these. 1/2 the apothem times the perimeter. The equation itself, the formula itself, is very simple. But finding the missing pieces becomes a lot more cumbersome for some of these. All right, and we were able to do this one because it was one of our special right triangles. It created a 30, 60, 90 triangle because of the fact that this was a hexagon. And as you kind of think about this, really every hexagon is going to work the same way. So if you run into another hexagon, you automatically know that it's a 30, 60, 90 triangle. Okay? And as you start to do lots of these, you're probably just going to start to recognize some of these common ones. Okay? Same thing with this one, the pentagon that's up here. If you were to break that down in terms of the angles, every pentagon is going to break down the same way. All right. And so as we start to explore some of these from the perspective of angles, finding and using that to find the apothem, you're going to find that you're going to see some of these angles repeat over and over again. Okay. Because every hexagon will have the same angles. Every regular pentagon will have the same angles. Every regular octagon will have the same angles. All right. They won't all be special right triangles, but we'll be able to use trig functions in order to find some of those missing pieces moving forward. Okay. So for right now, regular polygons, the radius goes from the center to the vertex. The apothem is that measurement from the center to the side. the formula for any regular polygon to find the area, you can always do 1/2 the apothem times the perimeter. Okay?